Welcome to this how-to video. The goal of this video is to read out the process value of an I/O link sensor with a S7 Profinet PLC from Siemens. In this presentation, we will use an 05D100 photoelectric distance sensor from IFM and the TIA portal software for the integration. First, we will establish the connection between the I/O link master and the PLC. Then we configure the I/O link port of the master to which our sensor is connected. After these steps, we will do the necessary programming to read out the process data of the photoelectric sensor. Before we start, here is a list of the necessary hardware and accessories. First of all, we need a notebook or PC with TIA portal installed. TIA portal is the automation software from Siemens that we use to program our PLC. We also need the following hardware: a PLC with Profinet field bus interface, for example a S7-1200, an AL1100 I/O link master from IFM, also with Profinet interface, and an 05D100 photoelectric distance sensor from IFM. Additionally, a 24V plug-in power supply, an Ethernet switch, and the corresponding connection cables are required. Now let's take a look at the hardware setup of our components. The Siemens S7-1200 PLC and the switch are powered by 230-volt AC main voltage. For the AL1100 I/O link master, we use a 24-volt plug-in power supply. The 05D is connected to port 1 of the master via an M12 cable. A switch is used for network communication between the PLC, master, and notebook. For this reason, 2 Ethernet cables are used to connect the computer and PLC to the switch, and an M12 RJ45 network cable is used to connect the AL1100. Last but not least, we need a notebook with the TIA portal software installed. Besides the hardware, we also need some software and auxiliary tools to make the whole process work. As mentioned in the previous slides, TIA portal is the programming software for the S7 PLC from Siemens. It brings the hardware and the software world together. The GSDML file of AL1100 describes the I/O link master in the PLC. It adds the master to the hardware catalog in TIA portal. In order to read the process data from an I/O link sensor, we need to know how much memory space to reserve for it and which data is transmitted in which order. This information can be found in the IODD file of the sensor. IFM also offers startup packages for download on its homepage. In addition to the GSDML file, these packages contain program examples, how-to videos, and the operating instructions. Once we have installed all the necessary software and connected all the hardware, we can start the configuration. The first step is to set the IP addresses of the notebook and the Siemens PLC. They must be in the same network segment. Open the Network and Sharing Center and navigate to the properties of Ethernet 2 to change the adapter settings. Set Ethernet 2 to the mentioned IP address of 10.1.1.30 and the subnet mask to 3 times 255.0. If you don't have administrator rights on your notebook to change the adapter settings, please contact your IT department. When we start TIA portal and create a new project, start by specifying the CPU of the automation device we are using. As previously mentioned, we are using an S7-1200. This PLC is equipped with a CPU 1212C AC-DC relay. The exact article number can be found directly on the PLC and is selected here as required. Then specify the firmware version. Here it is recommended to select the latest firmware version in the pull-down menu. In a new project, the device name is automatically given as PLC1. Of course, you can change it if necessary. Let's start by checking the communication between our PC and the PLC. To do this, we select the PLC and navigate to the properties. We change the IP address of the controller to 10.1.1.1 so that it is in the same network as our PC Ethernet port. Then write this change to the controller using Download to Device. The network scan automatically displays all compatible devices. Once the controller has been selected, the program can be transferred. Please select Stop All Modules in the pull-down menu, and the transfer will start. Communication between the PC and PLC can then be started using the Go Online symbol at the top. If everything is configured correctly, green checkboxes and circles will appear in the menu on the left-hand side. If you receive an error message, check your hardware and software network settings and download the program to the PLC. If everything is correct, please log out and we will go on with our configuration. Now switch to the network view of the TIA software, where the Siemens PLC is currently the only element. New network participants can be added using the catalog on the right. As only Siemens devices can be found here by default, start by adding the I/O link master from IFM that we are using. To do so, install the GSDML file of the master, which can be found on the IFM website. Let's see where we can find it. Open a browser and go to ifm.com. Select the country you are in and accept the cookies. Just register once on the website and log in with your account. You will then have free access to the download. Search for the AL1100 I/O link master. Go to the download section and scroll down. Download the GSDML file to your PC. The corresponding GSDML file is part of a zip file that we need to extract. As you can see, it's a package of files for multiple I/O link masters. Now add the I/O link master to the device catalog. In the TIA portal, under the menu item Options, implement the GSDML file for the I/O link master. The according GSDML file is part of a zip file that we need to extract. And as you can see, it's a package of files for multiple I/O link masters. These GSDML files are device description files for the I/O link master. Once we have installed them, we can select and use them as devices in TIA. In the network view of TIA portal, add the I/O link master to the PLC. From the hardware catalog on the right, we select Other Field Devices and go to the Profinet I/O section. Select the AL1100 from IFM and drag and drop it onto your network. Now use the mouse cursor to establish the Profinet connection between both devices. As you can see, here you have to go to Not Assigned on the I/O link master and select the device you want to connect with. In our case, it is the Profinet interface of the PLC. When a device is selected, its settings appear at the bottom. We can use these to manually adjust the IP addresses of the I/O link master and the PLC if necessary. Make sure that your computer is in the same IP address range as the PLC and the I/O link master to establish communication. In our example, we keep the IP address of the I/O link master, which is automatically adjusted after the IP of the controller is changed. Last but not least, assign a Profinet name. In this case, keep the auto-generated name. The Profinet name is mandatory for a Profinet network. If there is a device on the network that has not been assigned a name, you will get an error message. Before we go on, we check if all settings are correct. Load the configuration into the PLC and log in. If everything is configured correctly, all the icons on the left will be green. Else please log out again and check your network settings and the Profinet name. Now we come to the port configuration for the connected sensor using the example of the 05D100 photoelectric sensor from IFM. After the logout, we change to the device view of the I/O link master. In the device overview on the right, next to the device, we see the ports of the master to be configured. As we know from the hardware setup, the 05D100 sensor is connected to port number 1. Now we have to know how much memory space must be reserved for the sensor. Therefore, we should check the IODD file of the sensor. We can find the IODD of the sensor on the IFM website. By the way, IODD stands for I/O Device Description. Just enter the article number of the device in the search bar and navigate to the online datasheet of the 05D100 photoelectric sensor. In the download section, you can find the IODD in PDF format. When we open it and scroll down to observation, we can see how much data the sensor transmits and in which order. The sensor sends 1 word or 2 bytes of processed data to the controller. From left to right, the first 14 bits stand for the measured distance value in centimeter, the last bit for the switch point, or 1 for on and 0 for off. 3 unused bits are in between. Back in the device view of our I/O link master, we can now configure the ports. From the hardware catalog, drag and drop the data type 2 byte input plus PQI onto port 1 in the device view. The address is assigned automatically and can be adjusted manually if necessary. The PQI, which means port qualifier information, is a diagnostic byte that is also automatically appended to the process data. But we won't use it. Ports that are not required should be set to disabled, which is also done using drag and drop. Set the configuration of port 1 to no check and clear so that every I/O link device is automatically detected. After downloading the configuration to the PLC, check whether and how the data comes in. The next step is to read out the raw data from the 05D100, which is contained in the 2 bytes, 1 word, of process data, as we could see in the IODD PDF file. To figure out the address of this data, change to the device view and look at the overview next to port 1. In our example, the input address starts at 68 and ends at 70. As we remember, 2 bytes are reserved for the process data, which means bytes 68 and 69. Additionally, 1 byte at address 70 is reserved for the PQI, the port qualifier information. TIA offers a watch table for viewing variable content. Enter the start address of the sensor's process data. As the process data is stored in 2 bytes or 1 word, we read both bytes directly using the syntax %IW68. Additionally, change the display format of the word to decimal so that we can compare it to the real distance value. Last but not least, activate the watch table with the glasses icon at the top. When you do this and you are logged in, the current value is shown. You can observe the O5D's raw data change in parallel with the O5D's distance change in a camera image and see that it doesn't match with the distance value in centimeters on the O5D's display. The reason for this is that the word also contains 3 unused bits and the switch point of the O5D. Bits 4 to 15 then contain the distance value in centimeters. To get the distance value in centimeters, move the sensor data by 4 digits to the right using an SHR block. Let us take a closer look at how this is programmed. For the wiring of the SHR block, first create 2 tags with real names for better understanding. Name the raw data of the O5D sensor O5D input. And the result of the operation is then written to a distance variable. The distance value will be written in a marker addressed with IM68. For the small programming step, click on OB1 and change the programming language to FBD, which means Function Block Diagram, for a better overview. Select an SHR block on the right. SHR stands for Shift Right. As you can see, the data type of the function block is set to integer, as with the variables we have created. Furthermore, the data to be shifted is specified at the in input of the block or our raw data of the O5D input. N stands for the number of bits by which the input data should be shifted. As mentioned above, the result is then written to the marker word we have created with the name distance. Finally, upload everything to the controller. Before we take a look at our watch table to check the values, let's see what happened with the SHR operation in detail. For a better understanding, we take the process data structure of the O5D sensor and fill it with a numerical value shown in TIA portal. When the sensor shows a distance of 13 centimeters on the display, the raw data in %IW68 will show a decimal numerical value of 209. This value is shown here in binary form. This is not yet the current distance value, because it still includes bit 0 for the switching output of the sensor, as well as bit 1 till bit 3, which are unused. The SHR function block shifts the first 4 bits to the right. The 4 gaps on the left are simply filled with zeros. The result is named distance. If we now read the value again in decimal format, the result is 13 centimeter. Let's check our operation in the watch table. We enter the distance value in decimal format into a watch table to be able to read the value in centimeter, as well as the switch point at the bit address I69.0. By the way, the switching point is set to a value of 50 centimeter. We can see the changes in the watch table parallel to the sensor display. Now, the distance value shown on the sensor's display matches to the value in the watch table, and we can see the switch point at 50 centimeter. In this example, more than one piece of information is stored in a word, and some programming is required to make it readable. I/O link sensors of the latest generation have organized their process values in such a way that they can be addressed directly and read out without any further programming. Let's take a look at another photoelectric distance sensor that uses such a profile. Here you can see the IODD of an OGD photoelectric distance sensor from IFM that contains 4 words in total. In this case, the distance value can be read out by directly addressing the whole word. In addition, this sensor outputs information about the reflectivity of an object, which can also be read out directly by addressing the corresponding word. Here we use the previous project and connect the OGD distance sensor instead of our O5D distance sensor to port 1 of our I/O link master. As the IODD of the OGD sensor shows, we need a different configuration of the port. Select 8 bytes plus PQI information to be able to read both the distance value and the reflectivity. For a better understanding, we create 2 variables in the tag table. The distance value is read in at the start address, IW68, and the reflectivity at IW72. Once created, we add these variables to the watch table to see their values. Both are displayed in decimal format, so that we can compare them directly with the values shown on the sensor display. Last but not least, log in and upload the configuration to the controller. Now we can see that both the distance value and the reflectivity value in TIA portal match those in the sensor display. Thank you for watching. See you at the next how-to video.